All right, this is grade 6, unit 1, lesson 13. And in this lesson, we're going to be moving to polyhedrons. And so what is a polyhedra? A polyhedra is like a polygon, only in three-dimensional. So polygon, we've been studying about polygons, flat figures like triangles or parallelograms and all that sort of stuff. So those are flat rectangles. These are all polygons. Well, if you take that polygon and in some fashion take some polygons and turn it into a three-dimensional shape, that's basically a polyhedra. And we're going to get into some details. So let's get started. So we're going to start with talking about what is a polyhedra, right? And so your teacher is going to give you a bunch of stuff, or parents and teachers, if you're the teacher, you're going to want to do this. You have all these black line masters, and you're going to want to use all of these because this is a really experiential activity where a lesson, really, where the students are starting to get a sense of what is a polyhedra and what is not. Now, just take a look at these things. All right, take a look at all these polyhedra and all these polyhedra and all these things that are not. What are you noticing? What are you noticing about a polyhedra? What does it take to be a polyhedra? Well, it doesn't have to look like a kind of like a sort of, I'm putting in air quotes, a normal shape like a cube. It can look pretty funky. And then when you look at what is not a polyhedra down here, well, that's kind of a, in quotes, normal shape. That's a ball, right? A sphere. And this is a box, with an open lid. So what is making a polyhedra? And what is making not a polyhedra not a polyhedra? And you're going to start to see that, all right, polyhedra all have straight edges. Everything right here is straight edges, where this guy does not have a straight edge. And this guy definitely does not have a straight edge. So what else makes a polyhedra a polyhedra? Well, a polyhedra has flat faces. These are all flat faces, nothing curved anywhere. Even these are all a whole bunch of triangles, very flat triangles. But then over here, you've got this sphere. And then the other thing that we're noticing, and then, of course, this kind of looks like it's like a ribbon or something, so it's curved and stuff. And then we see that this cylinder is definitely curved. And then the last thing that we kind of notice is that all of the polyhedra are closed figures, but this box is an open figure. So that's basically the kinds of things we're going to be noticing. Now we're going to talk about two words, prisms and pyramids. So parents and teachers, be aware that when you're talking with EL students, and really if you think about it, all of our students are academic English language learners. So we're not talking about just a small group of your students who are learning English as maybe a second or a third language. We're talking all of our students need to really focus on what these two words are. Treat all your students as academic English language learners, and this portion of your lesson is going to go a little bit smoother. So we're going to talk about the difference between prisms and pyramids, all right? And so here's some prisms right here. These are all prisms. Prisms. And then these are pyramids. All right, so what's the difference between these two? And parents and teachers, we're going to need to give our students some time to talk about it and think about it. And of course, the big key thing, and if you look, wow, this shape looks kind of like it could be a pyramid, but it's not. So we're going to want to give our students some time to think about, well, what is the distinguishing feature between prisms and pyramids? All right, so on question 2, it's kind of cool. Students are supposed to be thinking about, well, what nets can be folded to create pyramid P? And this is a beautiful shape called a tetrahedron, because it's got 4 faces, tetrahedron. And so the idea is their students are going to try and figure out, like, which one of these fold into a beautiful little pyramid, a tetrahedron. So the idea of all of this is for students to be authentically engaged in language using the words prism and pyramid, and beautiful, beautiful activity. And then last one, your teacher, meaning you, if you're the teacher, or your teacher, if you're a student watching this video, you're going to be given a polyhedron. And you're going to decide what kinds of shapes, polygons, do you need to make that polyhedron. So listen to the words that we're using. It's just crazy, the amount of vocabulary going on here. You're going to decide what kind of polygons do you need to create that polyhedron, and then you're going to actually try and create that net. So we're going to go up, and we're going to say, okay, let's say you've been assigned shape C. So there you go. There's your prism. That is not a pyramid. That is a prism. And you're supposed to talk about with your team, what shapes do we need in order, what kind of polygons, what flat faces do we need to construct this prism? And then let's arrange those pieces so that when we tape them, they form a net, a flat map like, so that when you fold it up, it creates this 3-dimensional figure. So basically, you're going to try and create, right here, a net like this, flat shape, so that when you fold it on its lines, it will create your prism that you've been given. Wow, it's kind of slow today. That's cool. All right, and let's move on. Assembling polyhedra. So we're continuing to practice our vocabulary. Now here, your teacher or you are going to give a net, an actual net of a polyhedra. Students are going to cut out the net. They're going to fold it, and they're going to make the polyhedra. And then the idea is to count your vertices, your edges, and your faces. So what are the vertices? The vertices are your points. Here's a point. 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 And way back there is a point. So those are your vertices. Your edges are your straight lines right here. These are your edges. And then there's one back here, and then there's one back here, and then there's one back here. And then what are your edges? Your edges are your front faces. That's a face. That's a face. That's a face. You get the idea. So the flat part is the face. So vertices, edges, and faces, and they're all super important to know the difference. But man, we are just talking about tons of vocabulary. So parents and teachers, consider making some sort of anchor chart or a vocabulary word wall that has evidence of examples of all these words, so that when students are grappling with the right word, they can kind of look over at that word wall. That's going to support them as they're having these authentic conversations about all the vocabulary. We're talking about edges and face and vertex. We're talking about polyhedron. We were talking about polygons. We're talking about prisms, and we're talking about pyramids somewhere. There's a pyramid, and they all, oh my gosh, and then we were talking about a net. So there's just so much vocabulary. I'm just in awe of this lesson. There's just so much going on. All right, now let's do a little bit of practice. Select all the polyhedra. All right, remember what a polyhedra is? It's got to have vertices. It's got to have straight edges, no curves, and it's got to be closed. So this is a polyhedra. Man, this is kind of busy, but it looks like everything is straight. It looks like it's closed. It looks like it's all a polyhedra. That's a polyhedra. That's not a polyhedra because we got some curviness going on. And that is definitely not a polyhedra, because it's got some curvies. It's a sphere. So is this polyhedron A prism, a pyramid, or neither? How do you know? So let's go down here. All right. So is that baby right there? Is that a polyhedra? Well, it's closed. It looks like it's closed anyway. All the edges are straight. And so I'm going to go with yes, it's a polyhedra. Woohoo! Yes. So we're going to go up here and say yes, it is a polyhedra. Now it says how many faces, edges, and vertices. I'm going to tell you, I have an easiest time counting the vertices. So let's count the vertices. But man, everybody has an opinion, so roll with it. So 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 vertices on that edge or that side of. It's kind of like a cylinder, isn't it? Like a soda can, but kind of funky because it's not curved. So it's 1, 2, 3, 4, 5, 6, 7, 8. So down here we had 8 vertices. So down here we're going to have 8 as well. 1, 2, 3, 4, 5, 6, 7, 8. So altogether, how many vertices do we have? It looks like we have 16 vertices. All right, and if we want to talk about faces might be the next one. So let's take care of the faces. So the faces, now faces are the ones, the flat thing, right? So we have a top here, and then we have a bottom down here. So we know that we've got 2 faces so far. And then if you look, between these 2 points, it kind of creates a long face, like down the soda can, so to speak. It's not a can because the can is curved. This is not curved. So we could see a face right there. And so we have another face here, another face going down the can, another face, another face, another face, another face, and another face. So in addition to the top one and the bottom one, we have this idea of 1, 2, 3, 4, 5, 6, 7, 8 more faces. So we've got 8 plus the top and the bottom. So that sounds like we've got 10 faces. Beautiful. Now we're going to do the edges. All right, so the edges, and I'm going to do some serious erasing here because it's getting a little crazy. All right, so the edges, you recall, are the, let's do purple. All right, the edges are the straight lines, right? So I've got 1, 2, 3, 4, 5, 6, 7, 8. So I've got 8 over here, which means I have 8 on the bottom of the can. All right, if this is the top of the can, then we have the 8 on the top and 8 on the bottom. And then we have these connectors. And the idea of these connectors, so to speak, happens at each vertice, at each vertex, I guess. So remember, we had a vertex there, and there. So we had 8 vertices, and that's where our line, our edge, emanates from, right? So we had 8 on the top, we had 8 on the bottom. So here's our 8 on the top, we had 8 on our bottom, and then we had 8 going around the can, so to speak. So that's 8 plus 8 plus 8. So by my calculations, that means we've got 24 edges. All right. Now, I don't know if they're going to go into this, but there's a wonderful Euler's formula that connects the edges to the faces to the vertices in a beautiful, simple little formula. So be looking out for it. We'll see if they talk about that in this curriculum. So number 3, Tyler said this net cannot be a net for a square prism. A square prism, because not all the faces are squares. Do you agree? Yes, we agree. If it's a square prism, it's got to be, well, no. Cube, square, rectangular prism. No, I'm going to go with square. I'm going to agree with Tyler. And you know what? If you guys don't like, I think a square prism would look like that, which would be we call that a hexahedron. or a cube. So this square prism thing is kind of tripping me out a little bit. I think I would call this a rectangular prism because it forms this rectangular box. It kind of looks like it goes up like that. So I don't know, man. I'm going to go with I agree with Tyler. All right, number 4, explain why each of the following triangles has an area of 9 square units. Well, we got to remember, man, I love this curriculum. The formula for the area of a triangle is base times height divided by 2. I love this curriculum because it's always spiraling and causing our students to remember everything they've already learned so far. So 2 different ways that we could think about area of a triangle. We could think of it as base times height divided by 2, or we could think of it as 1/2 times base times height. They both work. It's the same thing. Explain why each of these. So they're telling us the area is 9 square units. So we have to prove it, right? So to me, if I can find the formula and use the formula, I'm going to. So here's my base. Here's my height. Here's my base. Here's my height. Here's my base, here's my height. There you go. And if you can't remember the formula, you can always just count the individual squares inside the triangles. Looking good. All right, number 5. A parallelogram has a base of 12 meters and a height of 1.5. What is its area? So we got a refresher course. What the heck is a parallelogram? Well, it's got a base of 12 and a height of 1.5, and I'll just pretend. And remember, typically a parallelogram is going to look like that kind of shape, although technically a rectangle counts as a parallelogram. All right, and so we remember that the area of a parallelogram is simply base times height. So in this case, our base is 12, and our height is 1.5 units right there. We're going to multiply those things, and that is our area. A triangle has a base of 16 and a height of 1/8 inches. What is its area? Remember the area of a triangle. The formula for the area of a triangle is 1/2 times base times height. I'm going to choose this one today because I think the fact that we're using that 1/8 inch is going to make it a little trickier to think about dividing by 2. So we're going to do the 1/2 version, that version. So it's going to be 1/2 times 16 times 1/8. And we're going to do the math, and that's basically the same thing as 1/2 times 16 over 1 times 1/8. And look at that. Oh my goodness. We end up with 16 over 16, which is 1. So the area of that triangle is 1 square inch. That's kind of cool. A parallelogram has an area of 28 square feet and a height of 4. So remember, the formula for the area of a parallelogram is base times height. They're telling you that the area is 28. We don't know what the base is, but we know that the height is 4. So you got to do a little bit of division to figure out what the base length is. And then a triangle has an area of 32 square millimeters and a base of 8. So remember that the formula for the area of a triangle is base times height divided by 2. Or we could say 1/2 times base times height. But we know that the area is 32 square millimeters and the base is 8. So let's do the 1/2. So we've got 32 is equal to 1/2 times 8 times h, which we don't know because it says what is the height. Now we have to do a little bit of math. We can multiply 1/2 times 8, that's 4, times h is equal to 32. And we have to use a little bit of division to figure out the value of the height. All right, that's pretty straightforward. And number 6, find the area of the shaded region, show or explain your reasoning. So, oh my goodness, we've got this big old huge triangle with a bite taken out of it. So when I'm looking at these kinds of figures, I'm going to think about subtraction. I'm going to think about trying to find the area of the whole triangle, pretending that that whole triangle is complete. And then, once I've found the area of the whole triangle, I'm going to find the area of this little square right here. And then I'm going to subtract those two things. And that's going to be how I get the answer. So I'm going to leave that up to you to map out. Now, I've mapped out your strategy. Now go carry it out. Find the area of the triangle, find the area of the square, and then subtract. And ladies and gentlemen, that wraps up Grade 6, Unit 1, Lesson 13, tons and tons of vocabulary in this lesson. We had polyhedra, we had polygon, we had nets, we had faces, edges, vertices. Man, we had prisms and pyramid, tons of vocabulary. So students, if you're getting lost in all the words, make yourself some flashcards, map them out, put them out on the walls so that you can easily look and see what those words mean. Parents and teachers, be aware that this is such a vocabulary-rich assignment and lesson that students are going to be getting lost in the vocabulary, let alone being lost in the math. So have a great day.